What's up?
Yeah.
How's it going?
How you doing, bro?
Pretty good. How are you?
Pretty good.
Yeah.
I brought a bunch of people for you today.
Oh, really? Let's go.
Got you.
Thank you. Appreciate it. What's up, Cam?
Yeah.
What's up, Sid? You remember
What's
me?
up? Yeah, I remember. What's up, Arna? How are you doing?
How's it going? Good, good, good.
Good.
You're like my inspiration, dude. Just trying to
Really?
grind, get that 520 plus,
Yeah, I appreciate
Rough.
it. Yeah.
Yeah.
All right. Do you guys all want to mute your thing besides like because
Yeah, well, no, once he starts talking, we'll just mute this bitch.
how do I use this? Oh, got it.
Oh, sorry. I wasn't.
Uh, Yeah. But how's studying going?
It's pretty good, pretty good. Just first practice test like 2 weeks ago, but I take one on Saturday again.
Oh, nice, nice. So, when are you taking it again?
April 29th.
Oh, thanks. Coming up.
I know.
Yeah.
That's
Yeah.
It's just us. We got a nice little squad going here.
Yeah.
Oh, you can still hear me through the thing? I can hear myself through this thing, dude.
Wait, Samir, what's your username on the leaderboard for Flappy Dog?
No, it's like Lurd Kurd Mirror or
Yeah.
something. Dude, if I don't like get first place by the time my MCAT comes around, like I'm not like gonna like get the score that I want. I've like convinced myself of that. Like I need to like be like number one by the time like my MCAT comes
Really?
around.
Yeah.
Yeah, what's the game?
Dude, is there how many questions like are on there? Does it ever
Like 400.
does it ever okay? So if I do like all 400, will it like re-loop back to the beginning?
Yeah, so it's gonna loop. So it like random. It's like a random deck of cards, basically.
Okay, it's random. Okay. All
Yeah.
right, cool.
All right. Okay. So let's wait like a couple more minutes and then get started. Hey, how are you doing?
Don't listen to Abraham, dude. He sucks.
Oh,
I already got a 528 on my
that's great. All right, we'll be a few more minutes.
A lot of it is
Okay. So can everyone see the screen? All right, good. All right.
Yes.
So what's up, everyone? So we haven't had like one of these in a while, but like so it's the MCAT Max group tutoring session. And so how it's gonna work is we're gonna kind of like go through the background of a passage and go through like all the concepts you need to know to understand the passage. And then we're actually gonna walk through the passage. So, and if, like feel free to ask questions during any time. And so before we start, I have like a little icebreaker. So if everyone could go around, say like your name, what school you go to, and then the icebreaker is if you could travel anywhere in the world, where would you go? So
Okay, I'll go first. My name's Arnav. I go to VCU. I'm a junior. If I could go anywhere in the world right now, I would go see Playboy Cardi. That's where I would go.
nice.
I can go next. My name is Samir Nader. I go to VCU, and if I could travel anywhere in the world right now, I would go to Qatar because I was supposed to go there for spring break study abroad, but it got canceled. So
Oh,
Hi, I'm Cameron.
Hmm.
I go to VCU, I'm a biology major, and if I could go anywhere in the world, I would definitely go somewhere like tropical, like underground cave, water caves or something, go scuba diving.
yeah, that'd be sweet.
I'm Andy. I go to VCU, and if I could travel anywhere in the world, I would probably go to Mount Everest.
Oh, nice.
Hi everyone, my name is Krishal. I'm a junior biology major at VCU, and if I could go anywhere, it'd probably be Egypt.
Oh, that's nice. Go see the pyramids and all that.
Yeah, exactly.
Hi guys, my name is Devyani. I go to VCU. I'm a senior bio major. If I could travel anywhere, I would probably go to Hawaii because I always wanted to go there. Never been to.
Yeah,
You.
I've always wanted to go to Hawaii, but like I always hear people talking about Hawaii. I've never been.
Mm.
Hey, I'm Rana. I go to VCU, and I think I'd probably want to go to California where my baby niece lives. I miss her, so.
Oh,
Yeah.
nice. That's sweet.
Hi, my guy. My name is Momin. I'm a junior at VCU, and if there's one place I could travel anywhere in the world, it would be Italy.
Nice. I'm actually going there in June.
Oh, that's tough.
Yeah, I'm excited for it.
Hey, my name's Ashrit. I go to VCU. I'm a junior, and I could travel anywhere. Go to India because that's where my family is.
Yeah, sweet. Yeah, I haven't been to India in a very long time. I really want to go.
Yeah, I haven't been there since 16. It's been a long time.
2016, yeah, I haven't been there
7 years.
2010.
Yeah. Oh shoot.
Yeah,
You're
so
the real
really
one.
Yeah. So be cool. All right, is that everyone? Okay. All right. So, like I said, today's going to be like kind of like an organic chemistry passage. And this is like one of the, so if you have ever looked at like the distribution for what's on the MCAT, you'll know organic chemistry is like not really that big of a component on the MCAT, but there's like a few concepts in that small part that they like test a lot. And so like one of the major ones you need to know is like what a Grignard reagent is. And so has anyone ever heard of Grignard reagent if you've like taken organic chemistry?
Yes.
Oh, yeah. So basically, Grignard reagent is, it's the formal definition is an organomagnesium halide. So organo is just like means it's a carbon compound. Magnesium means there's a magnesium metal in it. And then halide is for halogen. So like halogens are like, examples of halogens are like chloride, bromide, iodide. And so Grignard reagent has all three of these components. So it has a carbon chain, it has a magnesium metal, and it's attached to a halogen. And so why Grignard reagents are so important in organic chemistry is because you can use them to attach carbons to each other. And there's really not a lot of ways you can do that in organic chemistry. So this is like one of the rare ways to do it. So that's why they're kind of important, and they're tested a lot in terms of organic chemistry on the MCAT. And so you'll see it in like your chemistry physics section. So the biggest thing to note about a Grignard reagent is that like the bond between the carbon and the magnesium, it's extremely polar. So it's almost as if the carbon has its own negative charge. And because the carbon has its own negative charge, it can serve as a nucleophile. So can anyone tell me what a nucleophile is?
Anything that
Dude,
wants to,
Go ahead.
anything that wants to give away its electrons.
Exactly, yeah. So it's like an electron-rich compound. And so the carbon has a negative charge, and it can go perform a nucleophilic attack on other compounds. So here in this picture, we have like a ketone right here. So this carbon can go attach the ketone and kick the electrons on top of the oxygen. And so if let's say we have this carbon and it adds to this ketone, what is the final compound going to look like? In this picture right here. Like what type of compound is going to be the end product of that?
And alcohol.
Exactly. Yeah. So we're going to have the R group add to this carbon, and then it's going to form an OH up here. And we'll get a better picture of that. And so if you have an aldehyde, so how many R groups does an aldehyde naturally have attached to it?
One, right? Like,
Exactly.
yeah.
So if you add another R group to it, what are you going to have?
Two.
And then so it's going to be an alcohol. So would it be, what type of alcohol would it be?
Secondary.
Exactly, secondary alcohol. So, and then let's say if you have a ketone, you're starting with 2 R groups, right? So if you add an R group to it, how many R groups are you going to have?
Tertiary, 3.
3. So you get tertiary alcohol. So that's what Grignard reagents mainly used for. And so this is like a overview of the mechanism. So remember we said our R group is like very electron rich, it's nucleophilic. So it can go and attack this carbonyl. And when it attacks this carbonyl, it's going to attach the R group to it, but it's also going to kick electrons on top of this oxygen, right? And that is what we call an alkoxide. So an alkoxide is the same thing as an alcohol, except it's just deprotonated. So the oxygen has a negative charge. So you're going to take, usually you're going to add some water or like an acid, and it's going to protonate that oxygen. So you're going to get an alcohol. So that is the like basic reaction of a Grignard reagent. Does anyone have any questions on that?
I have a question. Does the are there any considerations about the stability of the carbo anion on the negatively charged carbon after the MgCl or the MgX has like left?
I think it's pretty stable, I would say.
Okay.
Yeah. Because yeah, they use it a lot, so I think it's stable. Yeah. All right. Okay. So
Can
now
you remind me what an alkoxide was?
So alkoxide, same thing as an alcohol, except it just deprotonated, so you don't have an H on the oxygen, so it's a negative charge.
Okay, thank you.
Yeah. All right. So next, so then we can like kick it up a notch. So you can have an ester. So an ester is the same thing as like a carboxylic acid, except of having a hydroxyl group, it has an alkoxy group. So an alkoxy group is just an oxygen bound to a carbon. So here we have an ester, and so it has its carbonyl, and it has an oxygen bounded to a methyl group. Okay, and so it's the exact same mechanism, except this time we're going to add the Grignard reagent twice. So first step here, we add the Grignard reagent to the carbon. We kick the electrons on top of the oxygen like we did last time. But now we have this thing called a tetrahedral intermediate. And so it's called a tetrahedral intermediate because there's 4 bonds to the carbon, right? And so this is unstable. So it wants to kick this alkoxy group off. And now you have a double bond to the O. So you have a ketone, right? But we don't stop there. So now we add another R group and we kick the electrons on top of the oxygen, gets protonated, and now we have a tertiary alcohol. So can someone explain that mechanism to me? Or like take your best shot at it?
Well, I had a question actually. So the goal of this Grignard reagent is to make alcohol at the end, like it's not going to stop at a ketone.
So if you add 2 equivalents, so you would need 2 of these Grignard.
Okay, so you
Yeah.
okay, gotcha.
So you can alter how many you add based on what you want.
Okay. But I guess I can answer the question you were asking earlier. So yeah, the R group, that blue one at the top, it's gonna attack, push the pi electrons up onto that oxygen, making it negatively charged.
Yeah.
And then those pi electrons are gonna come back down and form the double bond, and then the OCH3 group is gonna leave.
Yeah.
And then same thing happens again, that R group attacks the carbon again, pushes the oxygen on top.
Yeah.
But now like we don't have a stable leaving group, I guess, per se. Like any of the R groups aren't gonna really want to leave, and then we're gonna give it an acid workup, and then the oxygen is gonna get protonated.
Yeah, exactly.
Okay.
All right. Does anyone have any questions about that mechanism? All right. So now we're going to be looking at some of the compounds we're going to be working with in the passage. So can anyone here tell me what the name of this compound is? So this one.
Phenyl bromide, I think.
Yeah.
I don't know. Yeah.
Exactly. And so this is just going to be phenyl magnesium bromide. All right. And so based on what we just looked at, this last picture right here, remember we had an ester and then we added 2 R groups to get an alcohol. Okay. And so what is our R group in this compound?
Phenyl ring.
Yeah, exactly. So if we add 2 equivalents of phenyl magnesium bromide to a mixture containing this ester, what is the final product going to look like?
So at that neocarbon, you're gonna have 1, 2, 3 phenols, right? Because you're attacking twice. And then there's gonna be an OH group. So it's C bonded to 3 phenyl groups and then an OH group.
Yeah, so that's how it would look like. Does that make sense to everyone? If not, feel free to ask any questions. Yeah, so this is what our final compound is going to look like. So, and then I also have the intermediate compound here. So our intermediate compound is going to be ketone, right? So first we're going to add one of these phenyl magnesium bromides to this. We're going to get a tetrahedral intermediate. It's going to kick off this OCH3 group, and we're going to get a ketone, right? But we're not going to stop there. We're going to add another R group to it, and we're going to get an alcohol, right? So that makes sense to everyone. And so, again, what is this type of alcohol?
Tertiary.
Exactly, yeah. And so, yeah. Okay. Now remember how we said we get like an alkoxide? So when we add these R groups, initially we get an alkoxide, it's deprotonated. So we always need to add some acid to protonate it, right? And so when we add acid, acid is usually like an aqueous solution. So it means it's watery. So when we add it, we're gonna get we're going to get an organic and an aqueous phase. And so this tertiary alcohol, which phase do you think is going to be in?
I would say aqueous because it's got a polar group to it, right?
So it has one polar group, but the thing is there's like 3 super non-polar groups attached to it. So because of that, it's going to be the organic phase. Wait, all products, tertiary alcohol.
The question. At what point can you discern between something having a polar group and being able to dissolve in polar, and then it having non-polar groups and it being overall non-polar? Like, where's the line that we can
So
draw?
when you're like separating stuff in organic chemistry, usually even if it has an alcohol or like it's usually going to be in most compounds are usually going to be in the non-polar phase, the organic phase, unless it's deprotonated. So a lot of times in organic chemistry, they'll like add an acid to make something protonated, or like add a base to deprotonate it. So like think of like a carboxylic acid, right? I can draw it on the screen. So carboxylic acid looks like this, right? Can everyone see that? Can you see the drawing on the screen?
No.
I can't.
You can't.
No.
Let me see. Now can you see it?
Yeah.
Yeah.
See now, okay. Okay, so this thing is, you would call this polar, but it's still gonna exist in the non-polar phase. That makes sense. What's gonna exist in the polar phase is if you remove the hydrogen. So it has a negative charge. If it's charged, it's gonna be in the aqueous phase. So this is gonna be organic. Or this is going to be aqueous. So if it's charged, it's going to be in the aqueous phase. If it's not charged, it's most likely going to be in the non-polar phase, even though it has this polar group here.
Okay. If there are multiple polar groups, would it still be in the
Even then, yeah, you would have to go with organic. So another example is like if you have an amine as NH2. Although NH2 is like polar, right? It's still going to be in the organic. But what you can do is you can add an acid to protonate it. So let's say it's NH3. And now because it has a charge, it's going to be in the aqueous phase.
Okay, thank you.
Yeah. So just easy way to remember is that if it's charged, it's going to exist in the aqueous phase. If it's uncharged, it's most likely going to be in the organic phase. Yeah. Okay. And so when we add the acid to protonate this, this thing is going to be considered nonpolar, so it's going to remain in the organic phase. And the there's going to be the watery aqueous phase, like the acid is going to create an aqueous phase. So you're going to have 2 phases. So we need to know that for the passage. So is anyone like confused about the difference between organic and aqueous phase? Makes sense. Okay. Okay, last slide before we hit the passage. So a lot of times whenever we create a product in organic chemistry, we want to confirm that we actually got the product we wanted, because you're just going to get a reaction mixture, but you don't really know what's in it. So what we do is we use like spectroscopy. And the most popular spectroscopy, or one of the most popular, is IR spectroscopy. And so you'll run your mixture through this machine and it will give you a bunch of random peaks. But the thing is, we know what each peak corresponds to. So each peak tells you what functional group you have in your molecule. And so two big ones that you want to know for your MCAT is you want to know alcohols have a peak, broad peak. Broad peak means like wider. It's not as sharp and narrow. So there's a wide peak around 3,100 to 3,500, right? And then you want to know carbonyl has at around 1,700. It's going to have a narrow peak. Okay. So those are the two most important ones to keep in mind. So if I gave you an alcohol, which peak would you expect to see on your graph?
Abroad around 3,000, 3,100 to 3,500.
Exactly. Okay. And so that's that for the background PowerPoint. So does anyone have any questions on the background PowerPoint? Grignard reagent, anything like that? No questions? All right. Stop sharing that. Can everyone see the passage?
Yes.
Okay, good. All right. So can someone read this first paragraph for me?
I can read it.
Thanks.
A chemistry class carried out a laboratory protocol. During part 1 of the experiment, the class prepared a Grignard reagent, phenylmagnesium bromide, from bromobenzene and Mg. First, they combined 0.05 moles Mg with 10 milliliters of anhydrous diethyl ether in the reaction flask. They then prepared a solution of 0.05 mole bromobenzene in 10 milliliters of the anhydrous ether, and added 2.5 milliliters of this solution to the existing solution in reaction flask. The students allowed the ether to reflux, warming the flask until a precipitate began to form.
Okay. So what's going on in the first paragraph? Like, what are they trying to make?
They're Grignard reagent.
Right. And so what do they use to make the Grignard reagent?
Bromobenzene.
Hmm.
Yeah, so the class prepared phenylmagnesium bromide, but they used bromobenzene and Mg to start to make that.
Exactly. Okay. And then could someone else read paragraph 2?
I got it again. Okay, so during part 2 of the experiment, the class reacted the synthesized Grignard reagent with phenylmagnesium bromide with methyl benzoate. First, they allowed the phenylmagnesium bromide to cool to room temperature and then added 0.05 moles of methyl benzoate to the bromide dropwise. During this step, 2 equivalents of phenylmagnesium bromide reacted with 1 equivalent of methyl benzoate, allowing the alkyl groups of the Grignard reagent to be added to the ester. They let the solution reflux for 30 minutes, followed by cooling it to room temperature. The class transferred the solution to a larger beaker with a stir bar and added 3m H2SO4 to the solution dropwise. The students were instructed to watch for a color change, which indicated the characteristic quenching of the Grignard reaction. The acidified reaction mixture was then poured into a separatory funnel, allowing for the separation of the aqueous and organic layers from which the reaction's final product could be isolated.
Okay, awesome. So what do they do in paragraph 2?
So they start the first step. It says the class reacted the Grignard agent, so the phenylmagnesium bromide, which we made in the previous step, with methyl benzoate.
Right.
So
yeah, and that's basically it. So they use 2 phenylmagnesium bromide. There's 1 ester. So remember, the first step, we add the R group. We kick off the alkoxy group, so we get a ketone. Then we add another R group to the ketone. We get alcohol.
So question, the methyl benzoate, that's the, like, that was a structure with the C double bond O. What was that again? I can't remember which one that was.
Let me draw it on the screen.
Because you have the, I was just curious, you have, where's the methyl group? I don't know why I'm blanking, but.
So this is what it's gonna look like. Let's call this. So that's what methyl benzoate is.
Right, okay.
So for everyone, so we're gonna add an R group. So we're gonna add one R group here. So we're gonna add this. We're gonna kick these electrons up here. Negative charge here. And then this is gonna collapse. So this is gonna kick off this thing. So what we're gonna get left with in our intermediate compound is a ketone. And so this hexagon with a circle in it is like a symbol for a phenyl ring. So we get a ketone as our intermediate, but then we add another R group to it. So we're going to add another R group to it. We're going to get an alkoxide. So this is going to kick up here, negative charge. But then we need to add a proton to protonate it. And when we do that, we get our final compound over here. So 1, 2, 3. Okay. That's bad. And we get an alcohol. So that's how we got our final thing. Does anyone have any questions about that? Any step of that?
Well, I did want to mention, so benzoate is just basically, it's like just benzoate is the non-protonated version of benzoic acid, right?
Exactly, yeah.
Yeah, so if you're non-protonating and methyl group, it's like technically the ester that we're talking about.
Yeah.
Okay.
Okay. So I'm going to erase that then. Everyone's got it. Okay. So the question 1, the final product of the student synthesis was so I just drew the final product at the end. So can anyone tell me what the final product was? Yeah, hey, tertiary alcohol, exactly. Good job. So solution, they give a drawing here. So they even give a diagram here. So we see created phenyl magnesium bromide. It adds twice, right? So first time you add here, you kick off this OCH3 group, you get a ketone, and then we add one more time and we get an alkoxide, which we then have to protonate. Okay, next question. Which of the following describes the final separation step of the experiment? Okay. So it gives us, there's two weeks, so it's either organic or aqueous layer, and they like kind of mix and match them. So we have organic being ether, or aqueous being ether, or organic being hydronium, aqueous being hydronium. So in ether, is that going to be, or we can easily eliminate at least two of them by figuring out which one's organic and which one's aqueous. So is ether going to be organic or aqueous? So I'll draw out what an ether is.
Organic.
Exactly. So which options can we just go ahead and eliminate?
B because it says aqueous layer composed of ether, and then C, which says organic layer composed of hydronium.
And so remember our compound looks like this. We have 3, I'm just gonna call this pH for phenol. So like imagine a ring. We have an OH group attached to it. So remember, this doesn't have any charge. So is it going to be in the aqueous or organic phase?
The organic phase.
Organic, exactly. So it's going to be A. So it'll be the correct answer. All right. And does that make sense to everyone?
Yes.
Good. Next question. So which of the following peaks on an IR spectrum would indicate that the reaction has been successfully completed?
A.
A,
Because that's the one that corresponds to an alcohol.
exactly. Yeah.
It's a tertiary alcohol. So
Right. And if I said, if let's say, what is this answer? What are they trying to hint at over here? For D.
carboxylic acid.
Yeah, carboxylic acid could be one, or like just carbonyl group in general. So like C double bond.
Okay.
Okay, good. Anyone have any questions about that?
Yes.
Mhm.
Let's say we were just looking for a phenyl group, or what stretch would that be in?
I'm not sure exactly. I think it's like around 1500, 1600. But yeah, I don't think it was in that. That one's like, it'll probably not be tested on as much.
Okay.
But you could always look it up online, like find a chart. And they'll give you the number, exact number. So you just have to look up like IR spectra table. And they would give you like, they would go through every single functional group and tell you. But like the biggest ones I would say are alcohol and carbonyl.
Thank you.
Yeah, no problem. Okay, that's correct. Last question. So this is kind of like some general chemistry, but it kind of forces you to look at the passage. So it says, during part 1 of the experiment, what is the molarity of bromobenzene after its addition to the reaction flask? So take a second to look back at the passage. Where does it talk about bromobenzene? So here it says they prepared a solution of 0.05 moles of bromobenzene and 10 milliliters of ether, right? So we can do some math here. 0.05 moles over 10 milliliters. So can anyone tell me how many liters is 10 milliliters? So we know
Like,
yeah,
101.
exactly 0.01. Good. 0.01 liters. Okay. And so that should give us 1 over 100, 5 molar. Okay. But we're not done yet. It says we're going to take 2.5 milliliters of this solution and we're going to add it to the existing solution. So we need to figure out how much was in our existing solution, right? So it says they had 10 milliliters in the reaction flask. So we're adding 2.5 to 10. So what's going to be the total volume of our solution?
12.5.
12.5, exactly. And so we're adding 2.5 of our 5 molar solution. So we get 2.5 milliliters divided by 12.5 milliliters. So that's our dilution factor. So because we're taking 2.5 of our solution and adding it to another solution, we're diluting it, right? So you can kind of imagine it like this. You're taking, so this one already has 10 in it. And you're taking 2.5 from this one and adding it to this 10 one. So you're diluting this solution A, right? And you can figure out how much you're diluting it by dividing how much you added by the total, which is 2.5 divided by 12.5. So that's our dilution factor. Okay. And so now we just multiply our molarity of this solution that we took 2.5 milliliters from by our dilution factor to figure out the final concentration. So that would be 5 times 2.5 over 12.5. Okay. And so an important thing to note is that on the MCAT, you don't get any calculator for math. So most things the numbers should work out like properly. Like they should be easy to like cancel out or like calculate. So can anyone tell me what 5 times 2.5 is?
$12.5.
Right.
Yeah.
So what is 12.5 divided by 12.5?
1.
Exactly. So you can see how it like works out pretty nicely in terms of the math. So that way you don't need a calculator. So our correct answer is going to be 1. Yeah. And then that's, oh yeah.
Sorry, I have a question.
Yeah, no problem.
How did we know to multiply our dilution factor by our molarity? Is that just
So yeah, so dilution factor just tells you like how much your original solution is getting diluted. So you always multiply dilution factor by the original concentration.
okay? Thank you.
Any questions on that? All right. Well, that is the end of the passage. Yeah. And so like also one thing I want to is like if you haven't seen, I made this like MCAT game. It's like called like Flappy Doc. And so it has like 400 MCAT questions in it. And you can download it, you can play it. If you have an iPhone, you can play it. It's a pretty cool way to review content. So I think I sent an email about that, but like if any of you have any questions about that or want to know how to download it, yes. Or like who here has gotten a chance to play the game?
I played the game. I think it's
Same.
Yeah. Yeah, so the link it's on the website, but like go ahead, you can try to check out the game. It's a pretty cool way to practice. You can just compete with your friends. So it's like a fun way to study compared to just doing like passage practice and reading books and stuff like that. But if no one has any questions, I think we're done for the session. Yeah.
Thanks, Sid.
Yeah, no problem.
Thank you, sir.
Thank you.
Thanks, Sid.
Yeah, no problem. Thanks for coming.
We got to go see
Hey.
Cardi again soon, dude.
Oh yeah, for sure. Yeah, definitely.
That was so fun. I
Yeah.
was like, I always remember that night, dude. I can't believe I saw you there, you and Alex.
Yeah, it was.
I
a
was
great-
geeked because I'm just standing there and I looked to the left and you were like sweating and we were all like out of it. Oh my God, that was great. It was
Yeah.
amazing. That was fun though. We should do it again.
Yeah.
Trying to go to Rolling Loud maybe, but we'll see.
Yeah.
All right, man. See you
All
later.
right. Thanks for coming.
He's like,
Quick question, Sid.
Yeah.
So the dilution factor is just not like, I'm not wrapping my head around it.
Yeah.
So what is it? Is it just like the added solution over like the total?
Exactly.
Or-
Yeah.
Is that literally just what it is?
Yeah. That's what it is. So it's
Okay.
so we took 2.5 from one solution and we added it
Yeah.
to another. And so now our total was 12.5.
Okay.
If you divide 2.5 by 12.5, you figure out how much you're diluting it by.
Mhm.
And then you just multiply that times whatever your original was.
Okay.
And that gives you,
Yeah. And quick question. So the dilution, is it like derived from like any like other equation, like the M1?
yeah, so it's actually just, let me share my screen.
Yeah, go for it.
Let's see. So it's M1 V1 equals M2 V2. So it's actually just like a workaround of that.
Gotcha. Okay, that's what I assumed it was.
Yeah.
I just couldn't figure out like what was confusing me was I don't know why we didn't use like why wouldn't we use the 10 milliliters? Like why did we use 2.5 and 12.5? If that
Well,
makes
so because so the solution we were adding to, which we'll just call like B, was 10, right?
Gotcha.
And we added 2.5 to it.
Mm-hmm.
So because we add 2.5 to it, its volume's no longer 10. So when we do our total volume, we have to take that into account.
Okay.
Yeah.
Okay, so we can't consider. Oh, okay, that makes sense. Yeah, okay.
Yeah. So it'd be 2.5 or 12.5.
Okay.
And so that's how much you're diluting your solution by.
Okay, that makes sense. I appreciate that.
Yeah, no problem.
And thank you again for today. It really did help.
Yeah, no problem.
All right, you have a good day, man.
Hey, I had a question. Can you go to question 2
Yeah,
on
sure.
the same passage? Thank you.
All right.
On here, how did you like? I didn't understand or I missed. How did you get like the ether part like that? I got the organic part, but I didn't understand how you got the ether.
So it says here that let's see. So the whole reaction was kind of done in ether, right?
Oh, okay. Oh, okay, makes
Yeah.
sense.
And so
I was
ether is like, oh yeah, but yeah, so ether is one of like the most common like organic solvents. So that's how we know it's organic. Yeah.
Oh, okay. Yeah, I was just like, where did they come from?
Oh yeah.
But-
They mentioned in the passage that that's where. Yeah.
Oh, okay. Yeah, thank you.
Yeah, no
Also,
problem.
when would be your next session? Would it be like April 20th?
So I don't have a set date right now.
Okay.
But, do these times usually work for you? Monday at 7?
Yeah.
Okay. Yeah. So
Yeah,
I think,
'cause
yeah.
if it's like on April 20th, I would have finished my like MCAT.
Oh, okay. Yeah.
Just I'm asking.
Yeah. So I'll try to have more sessions like in the next few weeks just because what's up? Yeah, so I'll try to have more sessions in the next few weeks just because I know people are testing in like April, so it'd be probably
Okay.
so maybe we'll happen next. Are you free next week?
Yeah, I'm just doing MCAT, so if it's
Oh,
for
okay.
MCAT, I'm kind of free.
Yeah, so the big thing is just getting people to show up. So
Yeah.
definitely. I'll try to host one next week.
Yeah.
But I'll just watch your email and I'll definitely always reach out via email to let you know.
Okay.
Yeah.
Thank you.
But thank you for coming.
Yeah.
All right. Have a good day.
You too.